What we use the junction rule for is really to reduce the number of unknown currents. So if you take a look at this circuit right here, we have some potential sources and we have 3 resistors. Each of these resistors is going to have a current associated with them, so R1, R2, and R3 all have I1, I2, and I3 associated with them. So we have essentially 3 unknowns. What the junction rule allows us to do is say, at this junction A, I have essentially I3 leaving, so I'll make that the negative. Going into it, I have I1, and I also have I2 going into that. So all of these guys must add up to be equal to 0, so I can rewrite I3 as being equal to I1 plus I2, essentially allowing me to reduce the number of unknowns that I have, making it an easier equation to solve. So here I've replaced I3 by I1 plus I2. So let's get cracking on using some of these guys, and we'll start with just a simple circuit that you could actually just reduce by hand, but let's do it using Kirchhoff's rules to get some practice for them. So here we have 2 batteries, essentially a dead battery and a live battery. The live battery is 12 volts, the dead battery is at 4 volts, and we have some internal resistance, some resistance in the wires, so on and such forth. Well, let's take a look at the direction that our current is going to flow. Obviously the 12 volt battery is going to have a current that flows in that direction right there, and then you can kind of imagine it overpowering the current of the 4 volt battery, so essentially flowing through it. So that's going to be the direction of my current travel. Now let's just kind of set up our loop to kind of go in that same direction just to make it a little bit easier. Now let's start up with our loop. We don't have any junctions, so we don't need to apply the junction rule. We can say that the sum of voltages, sum of potentials must be equal to 0 for this loop. So let's just go ahead and pick my starting point to my loop to be right there. The first thing it's going to do is it's going to cross that 12 volt battery. Is it positive or is it negative? It's going from the negative side to the positive side, so it's gaining potential. Next thing I do is I go across this resistor right here. I'm traveling in the same direction as my current, so I'm going to lose my current multiplied by my resistance. That's going to be my voltage drop. Now I'm traveling right here on the 3 ohm resistor. I'm going in the same direction as my current. My loop is going in the same direction as my current's traveling, so I'm going to lose I multiplied by 3. Go through the 4 ohm resistor right there. I'm same direction as the current, so I'm going to also lose I times R. I go against the flow of my 4 volt battery, so I'm going from the positive side to the negative side, so I subtract 4 volts off right there. And then lastly I go through this 7 ohm, also in the direction of current travel, so I'm going to minus 7 multiplied by I, and all of these guys darn well better add up to be equal to 0. So what I'm left with is 12 minus 4, I have 8 volts. And then let's see, I have 7, 10, I got 16 multiplied by I, that must be equal to 0. And I can solve for my current, it must be equal to 8 over 16, or 1/2 of an amp. Let's take a look at a more complex looking circuit with a couple of junctions. So here we have a circuit, they're kind of nice, and they've given us a couple of the currents, a couple of the resistances, but we're looking for the potential from that battery as well as that resistance. So let's take a look at first the junction rule. Let's look at point B. Here we can see we have 2 amps leaving the circuit and 1 amp also leaving the circuit. So really we must have 3 amps flowing into the circuit from this side. So that tells us immediately that the current, unknown current, must be equal to 3 amps, so that's this guy right here. Now let's go ahead and solve for this resistance right over here. To do this I need to look at the loops that I can make. I can make one solid loop right here, I can make one solid loop right here, and then I can make the loop number 1 right there. Again, I can pick any of these loops that I want to use and say that the sum of potential must be equal to 0 along any of these 3 loops. Obviously, loop number 2 here is not going to help me solve for this resistance. Loop number 3 here, well, I don't know what this potential is, so I want to use loop number 1 to solve for that resistance right there. So let's choose right here as my starting point and start going in the direction as shown right here. First thing I'm going to do is I'm going to go from the negative side to the positive side of that battery and gain 12 volts. Then I'm going to be going with the current, so I'm going to subtract off the current multiplied by the resistance, the voltage right there. And then I keep on going along, chugging along, and then I hit that resistor going again in the same direction as current, or my loop going in the same direction as my current, so it's going to be a minus 2 times 3. And I kind of come back to my original starting place and I say, okay, all these guys must add up to be equal to 0. And so that tells us that this resistance right there must be equal to 2 ohms. Now we want to go ahead and solve for that unknown EMF. Now to do that, we could choose either loop number 3 here, now we know everything in that loop, or we could choose loop number 2 right there. Let's just go ahead and say I'm going to use loop 2, and I'm going to start off right here, and I'm going to go from the positive side to the negative side of that resistor. So my sum of my voltages is going to start off with a nice little negative EMF. Now my direction of loop travel is against the current, so I'm going to now add that 1 amp multiplied by 1 ohm. Continue on my loop. Now I'm traveling against, or now I'm traveling in the same direction as my current, and I'm going to subtract off then my 2 amps multiplied by 3 ohms, and then I can make my way back to my starting point, and I solve for my EMF. These guys must all add up to be equal to 0, so I come out with a negative 5 volts. So let's take a look at the most important complex network, and this is going to be critical for you to understand. If you can understand this example, it's example 26.6, then you're pretty much good to go on Kirchhoff's rules, but you really need to pay some close attention. So the first thing we're going to do is we're going to define the loops. We have loop 1, loop 2, and loop 3, and we could also do a 4th loop if we really wanted to. And what we're looking for is we're looking for the currents. So what we can do is we can also first start off by saying, we're going to have this battery right here, the current's going to flow in that direction right there. It's going to hit point C and it's going to split into 2 currents, and we're going to call that I1 and I2. So what we can see right here is we can write this current right there as I is going to be equal to I1 plus I2 using the junction rule. We're going to hit this junction right here. We're going to have I3 split off from it. So what we're left with is we're left with I1 minus I3. At this junction over here, we have I2 coming in and I3 coming in, so we're going to have I2 plus I3. Then we're going to work our way back right here. I3 is going to cancel out with negative I3. So we've simplified, rather than writing I4, 5, and 6, now we have some simplification. Now we're going to go around all of these loops. So let's go around loop 1, and let's start right here. Here we're going from negative to positive, and so we're going to write positive 13 volts. Now we're going to go across this resistor right there with I1 on it. We're going in the same direction, so we're going to write minus I1 multiplied by the resistance. I'm going to come down right here, still going in the same direction as the current, so it's going to be a minus. We're going to have the current multiplied by the resistance, and we're going to work our way back to our starting position. Please make sure you go through and verify loops 2 and 3. Make sure you can understand where the negative signs should and shouldn't be. That's going to be the biggest confusion on Kirchhoff's rules. So let's talk just very briefly once again about measuring current and measuring voltage. we measure current with an amp meter, and I've already said this, but I'll say it again. An amp meter is going to measure the current passing through it. So the current is actually physically going to pass through the amp meter. A voltmeter is going to measure the potential difference between 2 points. Nothing is going to necessarily pass through it. So here we have some current coming into some circuit element, and you hook one side of the voltmeter to one side of the circuit, one side over there, and you measure the potential difference. There's not going to be anything flowing through it. We can use these guys together to measure current and to measure voltage. From that we can calculate resistance and power, and in general this is the preferred method to do it. You just measure the potential across your load and then you measure the current coming out of it, rather than measure the potential from there to there, just in case the amp meter has any resistance that's messing up your measurement. You could also measure resistance directly using something called an ohm meter. I don't think we're doing that in this class. And lastly, there's something called a potentiometer that's going to measure the EMF of the source. So lastly, let's talk about finally hooking up resistors and capacitors together, essentially creating these things called RC circuits. So if we consider a circuit that kind of looks like this, where here we have a battery source, we have an open switch, so no current is going to flow. We're going to have a resistor here and a capacitor right here. Now we go ahead and we close the switch right there, and essentially what's going to happen is current's going to start to flow. It's going to be flowing away from the positive edge of the plate. But you might be saying to yourself, well, you know, wait a minute, there's a gap in the circuit, there's a break in the circuit, how can current be flowing? Well, if you think about when we just charged up a capacitor, what we were doing was we were using the potential to put a charge, a negative charge on one plate and a positive charge on the other plate. And really the same thing is happening. Here we have some positive charges that are flowing through this resistor right here and accumulating on this plate, and similarly we're getting some negative charges moving essentially that way. Negative charges move that way, current flows this way, piling up on this positive plate over here. But it actually turns out that as we get more and more and more charge on the capacitor, it becomes harder and harder and harder to charge it up. It's got some electric field that's fighting the buildup of charge. So if we were to go ahead and look at the graph of current versus time, you're going to see kind of some initial current flowing through the circuit, and then it's going to slowly die off as the capacitor becomes harder to charge. We can go ahead, we can express that current mathematically. It comes in the form of an exponential, where the current is equal to some initial current multiplied by e to the negative t, that's going to be the time, divided by the resistance and the capacitance. This resistance and capacitance is going to have a special name. We're going to call that the time constant, and essentially that's when the current has decreased to 1 over e from the initial current. So that's going to be that corresponding time right there. We can also take a look at what the charge is on a capacitor. So here we're going to have the charge as a function of time, and obviously it's going to start off with a zero charge and it's going to build up to some final charge where no current is going to flow anymore. So we can write that charge to be equal to its final charge and then 1 minus e to the negative t divided by RC. And these are the equations that you'll be using if you're asked to find, say, what the current is flowing through a RC circuit after 5 seconds. And we have some time, we have resistance and capacitance. Could also ask for, you know, the charge on a capacitor after some amount of time, something along those lines. Discharging of a capacitor is going to look very, very, very similar to the charging of it. Here we have some capacitor, and it has some charge on it. We have a resistor right here. We have no battery source, and we have an open switch. Essentially what the capacitor is doing is it's storing energy in the electric field. This energy can be used. It can light up a light bulb, a resistor if you will. So we go ahead and we close the switch, and what's going to happen is charge is going to start to flow. These positive guys essentially want to be closer to those negative guys, and so current's going to start to flow. It's actually going to flow in that direction right there. The book says that I is negative, but I think that's confusing, so current's going to start to flow through that direction. We're going to have less and less and less charge on there. At some point, all the charges will have emptied off the capacitor, and the power will have gone to the resistor. So we could write our charge as a function of time to be some initial charge multiplied by the exponential e to the negative t divided by RC. Similarly, we could take a look at what the current would be. Here it's showing the current to be negative. You're going to have some initial current that's going to be very large, and then it's going to become smaller and smaller and smaller and smaller. So we could write our current to be equal to the initial current multiplied by e to the negative time divided by RC.